Okay, we've got, I'm just going to start a stopwatch instead of a timer on this one. In this video, we're going to work another example problem. So we've got about a 30-minute example, then a 15-minute lecture video, and then probably, I don't know how long this video will be, but we'll work another example problem. And that'll make a nice lecture 9 for us. So let's finish out, shall we? So continuing lecture 9, a little bit of theory before we start the next example problem. We finished up on the last video talking about the specific heat for ideal gases, and then we said that there's really not much change between one temperature to another for most gases. As long as it's not a huge temperature change, there's really not much change in the specific heat, either C sub P or C sub V. So we can basically use a linear approximation and say, well, if I take at the average temperature, whatever C sub P or C sub V would be at the average temperature, then that gives me a really good approximation for whatever the shape the curve actually takes between point 1 and 2. And so it's a really close approximation. So if I integrate, for example, from T1 to T2, C sub V dt, that's equal to delta U for an ideal gas. Well, if I assume that C sub V is constant at the average temperature and it comes out of the integral, then I'm integrating dt. And so I can say, well, C sub V at the average temperature times the change in temperature will give me a good approximation for the change in internal energy. And we can do the same thing for enthalpy. I can say C sub P at the average temperature times the change in temperature gives me a really good approximation for delta H. So with that, I've written here that this is 464. I don't think this is still 464. It's probably 460 something. But all the same, it's an example problem. Let's look at this example problem, shall we? Excuse me. Let's organize our given information here. So yeah, I'm going to write this down and then I'll switch to the camera here in just a second. I have 20-pound mass. My substance is air. 20-pound mass of air. They've given me a pressure and a temperature. P1, 50 pounds per square inch absolute. Pound force per inch squared absolute. T1, 80 degrees Fahrenheit. We're going to heat this air up until the pressure doubles. P2 is equal to 2 times P1. We want to find the volume of the tank, and we want to find the amount of heat transfer. I'm going to call it heat in. Why do I call it heat in? Well, because they told me it's that we're going to heat it up until the volume, or so I'm sorry, until the pressure doubles. Now, there's something else that's given to us here that's not like a number. Taking a drink there to give you a second to look at it and think about what have I missed here. Maybe you remember from a previous video, I said, always look at your adjectives. What do your adjectives tell you? What do your adjectives tell you? What is this right here telling me? I have a rigid tank. Rigid tank tells me the volume is constant. Rigid meaning not deforming. A lot of times in like a statics or a mechanics class, a rigid structure means that it's not deforming. We'll leave that until like a mechanics of materials or strength of materials class where we actually start considering materials that deform. But if it's rigid, we're assuming that it's not deforming. So for our purposes, what that's telling us is we've got this stuff in a tank. We're going to heat it up. That tank's not going to bloat or expand or bubble basically. It's just going to hold its shape. So the volume is going to be constant. All right, I think I've got all the things here. I'm going to stop share for the moment. Okay, so now we get into, okay, well, what are some good tools to find these unknowns? We've got a couple of unknowns we're looking for. We're looking for volume, we're looking for heat, And a lot of times I'll tell the class, hey, which one do you want to go after first? What one do you want to tackle first? And sometimes some people will say, well, let's try the volume, and some others might say, well, let's try the heat. You know what? Let's try to find the volume first, shall we? If we try to find the volume first, all right, well, what are some good tools for finding the volume of this thing? And well, volume is a property. So we have to start going through a checklist of, okay, well, what tools do we have to find properties? Well, if it's water R134, we've got table properties, and they're very good. We could probably find the specific volume of the substance, and if I since I know the mass, I could use the mass and the specific volume to find total volume. The problem is this is not water R134. This is air. So that's not going to, the table properties in this case are not going to work. We do have tables for air, ideal gas tables for air, but if you look at those don't have volume. Older editions of the text will have a reduced volume value, but they don't, yeah, Izzy, I'm recording. I'm recording. We're busy. I'm sorry. Older tables will have reduced volume values, but they don't have specific volumes like water and R134 do. So I'm not going to be able to use table properties for this. So what's another tool that I might have for finding an unknown property like volume for something like an ideal gas like air? And I'll intentionally repeat, what could we use for some kind of an ideal gas like air? And I might continue to repeating that to the class. What if I've got an ideal gas? What should I use to find a property? And somebody eventually will say, "Well, what if you use the ideal gas law?" Okay, I like it. Let's use the ideal gas law. PV is equal to mRT is the version of the ideal gas law that we can work with. This is not the universal gas constant. This is the gas constant specific to our substance. PV is equal to mRT. Okay. What do I know here? I know pressure and temperature. Um, so I could use state one or state two, but let's just use state one. The mass and the volume are constant. It's a closed rigid tank. So constant volume, constant mass. I just need the R value. So I could find the volume easy enough, right? V is equal to mRT1 divided by P1. We calculate that. Okay. All right, so you can plug in numbers and go for it now, but you know what? Let's um let's continue on before we start grabbing numbers and pulling a calculator out and all the things. Let's see if we can set up a path to find our other unknown here. Right? So what's a good tool for finding an unknown heat transfer? And until you've got a junior level course in heat transfer, where we spend an entire 3 hour class really learning about different methods and models for finding heat transfer after you understand differential equations, really for us, we've got one main tool for finding heat transfer. It's the good tool that works for just about any unknown energy quantity, which is, go ahead, I'll go ahead and pause till you figure this out. What are we going to use to find heat transfer? Good. It's first law, right? Anytime I've got an unknown energy, especially heat, first law is probably our best tool for finding it. Step one of writing a first law equation, draw your system. Yay, system strong. Doesn't have to be anything fancy. It's just a rigid tank that holds air. That's it. So there's my system. Now we need to draw all the energies crossing the boundary. Okay. Well, I know I've got heat. I know I've got heat. Anything else? Well, if the volume changes, we've got boundary work. So basically, anytime I got a piston cylinder, there's going to be boundary work, or any other volume changing system, there's boundary work. But the volume's constant here, so no boundary work. There's no electricity. There's no other force being applied to this thing to do work. And if I'm looking for the heat in, I'm probably not worried about the heat out. So that's it. Right? The entire left-hand side of the first law equation simplifies down into Qn. That's in minus out. Well, there's nothing out. There's only heat going in. Qn, and it's a closed stationary system, so Qn is equal to m delta U. That's it. It's your first law equation. Right? Normally in a exam one type problem with me, that's going to count for like 10 out of 25 points, somewhere in the neighborhood. If it's right, if you've written your first law correctly and simplified it correctly, that's going to be a huge chunk of points there. So you want to be practiced and really good at very quickly writing out correctly your first law equation. Because if you can't, you're not going to be able to do exam 2 problems. You're not going to be able to do exam 3 problems or final problems. So there's a reason I gave you a checklist, and I'm going to tell you practice doing that. Okay, Qn, that needs to be my only unknown. I know the mass. That's given up here. Right? Mass. Delta U, U2 minus U1. Well, we know, we've seen previously, right? We will look at our PowerPoint notes. We know I can estimate delta U with a good C sub V average times delta T. So I could do this. I could say Qn is approximately M C sub V at the average temperature times the change in temperature, T2 minus T1. Okay. So that means now, what do I know? I know T1, that's given up here. Okay, I know T1. I don't know T2, so I'm gonna have to figure T2 out. And I need to find C sub V at the average temperature. So that's gonna take time. But it's not hard at all. We just have to get there. So to know C sub V average, I need to know the average temperature, which means I need to know T2 to find the average temperature. Fortunately, I think we can find T2. How can we do that? Well, what is temperature? Temperature is a property. Okay, so now temperature becomes my unknown that I'm after. All right, what tools do I have to find an unknown temperature? Because I've organized everything I know. So what's a good tool for finding an unknown temperature? Well, temperature is a property. I need to know what my substance is. I'm dealing with air. Okay, so I need to use the rules associated with air. Well, air is an ideal gas. Oh, I could use ideal gas. So I could say P2V is equal to M R T2. Now I don't know P2, but I do know P2 is 2 times P1. Since I know P1, I technically know P2. P2 would be 100 pounds per square inch. I can just simply double it because this A tells me this is an absolute pressure, so therefore I can double it. If it was a gauge pressure, I would need to add the atmosphere to it before I could double it. You can't just double a gauge pressure, but you can double an absolute pressure. Kind of like you can double an absolute temperature, but you can't double a Celsius or Fahrenheit relative temperature. Okay. All right, so I know P2. Okay. I could do this. And I could say, well, T2, I could do this. I could say, well, T2 is equal to, I'm sorry, I'm thinking while I'm talking here. T2 is P2V over MR. I'm going to have to find volume anyway. And so this works. A lot of solutions will also have you do, there's kind of a cheat here. It's not really a cheat because it's legal. But a really cool thing you can do here is you could say, well, you know what? I'm going to take P2 over T2 and say that's equal to MR over V, and that's equal to P1 over T1. What have I done? I've taken the ideal gas law and I've moved all my constants to one side of the equation. So if I move V, which is constant, to this side of the equation, and move the variables, which would be T, to that side of the equation, I've got P1 over T1 is equal to MR over V. So a common trick you can use the ideal gas law, if you've got a bunch of things that are constant, put all the constants onto one side of the equation, and then you can set all the variables on the other side of the equation, and that whatever that ratio of the variables is true then at all states, because these are all constant. So what this means then is that T2, which is what I'm looking for, then is going to equal P2 over P1 times T1. And since P2 is 2 times T1, I'm sorry, P2 is 2 times P1, this is just 2 times T1. And then I'll ask the class, so if I go this way, I'll say, okay, T2 then is going to be 2 times, all right, what is T1? And somebody will say, well, it's 80 degrees Fahrenheit. And I say, yeah, that's right. So what is T1? And I won't write down 80 degrees Fahrenheit because I can't use 80 degrees Fahrenheit. I can't just double 80 degrees Fahrenheit. Steve, isn't it just 160? No, it's not, because that's a relative scale. You can't double a gauge pressure, and you can't double a relative gauge temperature like Fahrenheit or Celsius. I have a temperature up here in Fahrenheit. This is not an absolute temperature, therefore I can't just multiply or divide this temperature directly. I can, though, however, if I add 460 to this, I get approximately Rankine. So 460 to this makes about 540 Rankines. And I can double 540 Rankines. I can't double 80 degrees Fahrenheit. I mean, you can, but it gives you a garbage thing that doesn't mean anything. But I can double that 540 Rankines, and this now becomes 1080 Rankines. And if I subtract 460 off of that, that is 620, yeah, which is 620 degrees Fahrenheit. Okay. Now, bottom of that page, let's go to the next one. L9, this is probably page 4 of 4. We'll say 4 of something for right now. Okay. Now, so how does this help us? What are we trying to do? I'm trying to find the heat transfer. To find the heat transfer, I need to know both temperatures. Now that I know both temperatures, I can find the average temperatures, which will give me C sub V. And that with the mass, which is already known, will give me Q. So I've got a path to that. And also, I was asked to find the volume. So you can find either one, not this one. If we go ahead and finish out finding the heat transfer, I guess we could go ahead and finish that out, right? So now I need C sub V average, right? So how do I find C sub V average? Well, to find C sub V average, I need to know T1 and T2, which I now know. That'll give me T average. My average temperature is 5. T1 is 540 Rankine plus 1080 Rankine divided by 2 is 810 Rankines. If I remove 460 from that, that gives me Fahrenheit, 350 degrees Fahrenheit. That's my average temperature. Why do I need that? That's going to give me C sub V average. The average temperature gives me C sub V average. Okay, so if I go now to the property tables, so this is table A to B. This is air at different temperatures. This one is in Fahrenheit, right? So you need to look, is it in Fahrenheit or Rankine? Is it in Celsius or Kelvin? Because I think the metric tables are actually in Kelvin, but these are actually in Fahrenheit. Notice I have a row for 300 and I've got a row for 400. I don't have a row for 350. So I know my average temperature is 350 Fahrenheit. I don't have a row for that, but notice what the difference would be. I'm halfway in between 0.174 and 175. I'm halfway in between those two. So what I'm going to do is I'm going to say, I'm sorry, 0.174 and 0.176. So I'm going to say my C sub V is 0.175, halfway in between those two. The units on that are going to be BTU per pound mass Rankine. Now, if I scroll up, notice that I could find air has a C sub V value of 0.171, which is not actually going to be right. It's going to be close. It's going to put us in the ballpark. It's 0.171 if my temperature was 80 degrees Fahrenheit. Notice my temperature is not 80 degrees Fahrenheit. I'm somewhere around, my average temperature is around 350 Fahrenheit, not 80. So this value does not help me. So I need to go to the next table here. And I'm between these two values. And I'm somewhere between those two values. Well, I happen to be halfway in between, so I'm just going to take a value right in between the two, no interpolation necessary, and we should be good to go. Now, while I'm here, notice if I might as well, while I've got the property tables pulled up, notice for my to find my volume, I need the R value. Where do I find the R value? R value is going to be in table A1. So while I've got it here, table A1, notice the R value has two different values for air in the English units, and it's true of all your, in all of the, so we're doing properties here. In the English units, for all of your ideal gases, you have an R value in two different units. They're both correct. Um, they're both correct, but for our equation back here, temperature is going to be in Rankine, pressure is going to be in PSI, and I want V to be in cubic feet. So I'm going to use this one that's got that unit set. Now, there's a lot of stuff later we're going to need the BTUs per pound mass Rankine, but for right now, I'm going to go ahead and record this one, 0.3704, and the units there are PSIA, pounds per square inch, times cubic feet, divided by pound mass, and also divided by Rankines. Okay. So to find that, I just need to know that I've got air, and that's it. It's the only thing I need to know to find the R value. Okay. So, like I said, you can find either one. We got to find both volume and Q. Find either one any order you like. Let's go ahead and find volume. Volume is going to be mass times this R value times T1 divided by P1. Okay. Volume. Mass. We said that was, if we go all the way back to the beginning, that was 20-pound mass. Times the R value we've just looked up is 0.3704. Units there are PSIA, cubic feet per pound mass, Rankine. Your textbook kind of spoils you by giving it to you in those units. It's not hard to convert from BTUs to PSIA cubic feet. Kind of like we saw a Pascal times a meters cubed is a joule. You can also, there is going to be a conversion for PSIA cubic feet to BTUs. It's not one-to-one like, Pascal meters cubed is 1 joule, but there is a conversion factor you can find. Anyway, that is mass times R. We need to multiply by temperature. So again, I would ask, okay, what's our temperature? What's T1? And maybe somebody would say 80 degrees Fahrenheit, but hopefully there's at least enough of the classes starting to catch on. I can't use Fahrenheit here because I'm multiplying by it. I've got to use Rankine. And notice also there's a Rankine here. So I got to cancel out with this Rankine there. So I've got to use a Rankine. I can't use Fahrenheit here. I could use Kelvin, but that means I got to convert everything to metric, and that's just silly. I'm going to divide by my pressure. My initial pressure is 50 pounds per square inch absolute. I guess I could pause here and shorten this video and run those numbers for you. And I guess I should say before I hit equals here, if you want to pause and run the numbers yourself so we make sure we're on the same page, that's a good exercise. Be able to use your calculator really well because you're going to need it for the exam. So pause here if you would like and go ahead and get me a number and see if we agree on this. Okay, you got it? I've got almost exactly 80. And the units left, if you look at them, the pound mass goes away. I've got PSI on top and bottom. Those go away. I've got the Rankines go away. I'm left with cubic feet. That's it. And that's what we want for volume. So that makes sense. That's good. Okay. Now what? Are we done? Well, no, the problem asks for two things. It asks for volume and QN. Okay. Well, I think we've got the tools we need to find QN at this point because we said I'm going to use QN is equal to mass times C sub V times delta T. Well, we already know T1. I've used the ideal gas law to figure out T2. And then now that I've got T2 and T1, I know my average temperature. Therefore, I know C sub V average. So therefore, I can find Q based on all of that information. So now my heat in is going to equal my mass of 20-pound mass and this is an approximation, by the way. 20-pound mass times my specific heat of 0.175 BTU per pound mass Rankine. I'm going to multiply that. You can either use Fahrenheit or Celsius here because I'm taking a difference in temperature. But I know both of them, or I guess Fahrenheit or Rankine, I should say. I could use Fahrenheit or Rankine. I know T2 is 1080 Rankines, and I know T1 was 540 Rankines. But again, you could write both of them in Fahrenheit here because I'm taking the difference, and therefore I would get the same value. Okay. If you want to pause here, I'll pause and get us a number. If you want to pause and work it out with me, go for it. All right, you got a number? If not, pause it. Here's what I've got. I've got QN as 1890. If you look at the units here, the pound mass goes away, the Rankines go away. I'm just left with BTU. That's a unit of energy, which makes sense. 1890. Okay. Now, if I go, I think I've got answers to this. So let's go look at my PowerPoint slides. Oh, there was the volume back there. Yep, volume, 80 cubic feet. So far, so good. Okay, so this is what I do. We have the middle one. We have 1890. We used C sub V at the average temperature. The average temperature between our known T1 and T2. That is a perfectly acceptable answer. This will get you all the points with me. This will get you some of the points, most of the points probably with me, where remember I said, let's not use table A1A. That's at like 80 degrees Fahrenheit. That's room temperature. We're not at room temperature. We're way beyond that. So this is not an accurate value. So this is not a good value. But notice it's to two, maybe three significant figures in agreement with my other answers. This is within three significant figures, essentially, of the best answer. This one's perfectly acceptable. This one's in the ballpark. It'll get you to most of the points. This will get you, the second one will get you all the points. This third one will also get you all the points. If you go look at table A17 in the property tables, right, table A17, that's the first ideal gas table. So that's ideal gas properties of air. And you have temperature here at different Rankines. You got a row for 540. And so you got a U value right here of 92.04. And you can go down here and maybe we got a row for 1080. We do have a row for 1080. And here we've got a U value of 186.93. And that's what we have here. And that difference, that would give you the absolute best value. So this works. The problem you can run into is you may have to interpolate, if you're between rows, you may have to interpolate one or both of these numbers. But all I need is just the temperature value for an ideal gas that will give me a U and an H value to go into my first law equation. All right, guys, that is right at 30 minutes, give or take. So that's this plus one lecture video plus a 30-minute example problem. That's a good 75-minute lecture. Let's call that good here. All right, see you guys in the next one.